MnCr2O4 is likely to have a normal spinel structure because the possible options are shown here. In normal spinels, all the divalent cations occupy one of the 8 available tetrahedral holes, and all the trivalent cations occupy half of the available octahedral holes. In inverse spinels, all the divalent cations and half of the trivalent cations are in octahedral, and other half of the trivalent cations are in tetrahedral holes. To confirm MnCr2O4 is normal spinal structure, we need LFSE, that is ligand field stabilization energy value of octahedral and tetrahedral geometry of the possible ions of manganese and chromium. The possible ions of manganese and chromium are Mn2+, Mn3+, chromium 2+, and chromium 3+. LFSE for octahedral can be calculated by using this formula, where P is the number of electrons in T2g orbital, Q is the number of electrons in Eg orbital. LFSE for tetrahedral complex can be calculated by using this formula, where X is the number of electrons in E orbital, where Y is the number of electrons in T2 orbital. The both LFSE value should be in same unit, that is delta 0. Delta T is equal to 0.45 delta 0. If we multiply this delta T value into 0.45, we get units of delta 0 of tetrahedral geometry. Now we have in doubt MnCr2O4 will have low spin complex or high spin complex. Usually oxide ions produce weak field, that is high spin complex like water molecules. Now let us discuss how LFSE plays in predicting the structure of spinels. Now we calculate LFSE for Mn2+. Mn2+ has D5 configuration. Its octahedral geometry is T2G3 Eg2. Its LFSE value for octahedral configuration is 0. Similarly, we calculate tetrahedral configuration and its LFSE value. Its value is also 0. Next, we calculate LFSE for Mn3+ and chromium 2+, both having D4 configuration. Its LFSE value for octahedral configuration is 0.6. Here we neglect the negative sign. Similarly, we calculate for tetrahedral configuration. Its LFSE value is 0.4. Its unit in delta 0 is 0.18. Next, we calculate LFSE for chromium 3+. It has D3 configuration. Its delta 0 for octahedral configuration is 1.2. Next, we calculate tetrahedral configuration of LFSE. Its value is 0.8. Its value is 0.36 in delta 0 units. Now we check out the answer. Here LFSE value is greater for octahedral geometry than tetrahedral geometry. So LFSE value of chromium 3+ is higher compared to all other ions, so it has most possible to occupy in octahedral holes. Now we check out the answer. that is in the first option, Mn2 plus will have a LFSE in the octahedral site, whereas the chromium 3 plus will not. Comparing this tabular column, Mn2 plus having 0 LFSE, so it cannot have LFSE, we neglect this answer. In the third option, Mn is plus 3 oxidation state and chromium is in plus 2 and other is in plus 3 state. These results shows it can form the inverse spinel structure, but the formation of inverse spinel for MnCr2O4 is impossible. So this is not correct answer. In the second and fourth option, manganese is in plus 2 oxidation state, chromium is in plus 3 oxidation state. In the second option, there is no mentioning of any LFSE value, so we neglect this option. In the fourth option, chromium will have LFSE. We check out here, chromium having higher LFSE, so it can occupy in octahedral site, whereas Mn2 plus having 0 LFSE, it occupy in tetrahedral holes. So MnCr2O4 have normal spinel structure. The fourth option is the correct answer. Thank you.